Welcome to the lecture on rising methods. So, in this lecture we will talk about different methods for the riser volume calculation. So, we have discussed in the earlier lecture that you require the sufficient amount of volume of liquid metal in the riser, so that it can feed to the casting in case of shrinkage. Now, the thing is that we know by using the Svorinov rule that T is proportional to V by SA square. Now, what does it mean? It means that solidification time will be proportional to volume by surface area square. So, suppose, there also we discussed that for riser this T should be higher, means the V by SA for riser should be higher than the casting. So, V by SA for the riser has to be more than V by SA of casting, because riser must solidify later than the casting, then only the riser will be able to feed the liquid metal to the casting. Conversely, if you take the surface area by volume of riser, then this has to be less than surface area by volume of casting. So, this is basically time of solidification. So, this will be basically proportional to the time of solidification. So, V by SA, and this will be the inverse of that. So, if this is more for riser, this has to be lesser for the riser, because if this value is higher, it will take less time to solidify. So, this has to be of the lower values. So, then again what should be the quantity of the riser amount, that is also important. So, as you know that rising requirement is because of the contraction or shrinkage which take place during the solidification, and we know that what is the typical amount of contraction values or shrinkage values, that is normally in certain percentage of the volume, and that varies from 3 to about 7%. So, if you know these percentages and if you know the casting volume, I mean you can say that at least this much of amount of liquid metal is required for the riser. So, both the things are important. You must have sufficient volume of the liquid metal in the riser, so that it can be fed whenever there is shrinkage in the casting. Also, this freezing characteristic condition should be satisfied. Surface area by volume of riser should be basically satisfied. I mean this should be less than surface area by volume of the casting. So, these are the conditions which should be satisfied. Now, let us take an example. Suppose you are taking a steel plate of dimension 25 by 25 by 0.25 centimeter. So, suppose you take steel plate of dimension 25 by 25 centimeter by 0.25 centimeter. Now, if you look at this plate, for this if you find the A by V, so A by V of casting, so A by V you can find it. Now, you can find it by A by V like 2 into 25 into 25 plus 25 into 0.25 plus 25 into 0.25. So, if that is calculated, that comes out to be 8.16 per centimeter. So, A by V of casting comes out to be 8.16, because V we know V will be 25 into 25 into 0.25, and A we can find it. Now, if we take suppose a cubic riser of dimension 1.2 centimeter, side 1.2 centimeter. So, if we try to find its A by V, so A by V of riser, so this A by V of riser, that will be basically, again we can calculate 6 into 1.2 into 1.2 divided by 1.2 into 1.2 into 1.2. So, it will be 5. So, again that's what we get in case of cubic riser. Now, the thing is, what we see here is A by V of the casting is 8.16 per centimeter and A by V of riser is again 5 per centimeter. So, what you see is A by V of riser is less than A by V of casting. The thing is that this condition is satisfied, but let us see whether it satisfies that on the aspect of quantity of the metal which is required. So, suppose if the 3% is the shrinkage amount, if shrinkage amount is 3%, shrinkage is 3%, volumetric shrinkage is 3%, let us say, in that case the amount of liquid metal required, in riser, that will be basically 0.03, 3% of the volume of the casting. So, casting is 25 into 25 into 0.25. So, basically that comes out to be, so if we take that, so that comes out to be about 4.68 centimeter cube. So, this is the amount of liquid metal which is required for the riser. Now, what we see, we have the riser, suppose you have selected the riser of cubic shape of side 1.2 centimeter. So, what is its volume? Now, volume of the cubic riser, that is coming out to be only 1.2 into 1.2 into 1.2. So, it will be 1.728 centimeter cube. Now, this is basically less than this, although it is satisfying the condition for the freezing characteristic, but the amount of liquid metal which is required, that is not sufficient. So, we have insufficient riser volume, molten metal. So, this sufficiency condition is not met. In fact, even you will have to have the volume more than this, because riser is also a casting and that will also solidify. So, for this much of volume required, you need even a larger dimension, larger configuration, so that it can release at least this much of liquid metal if required. So, this is very important, because that is how we see that why the risering is required, why a certain volume is required. So, we do not know what will be the volume of metal required. We can have another example. Let us say you have a cube of 15 centimeter each side. So, let us see that you have the aluminum of, so you have aluminum as the liquid material, and it is a 15 centimeter cube casting. And if you take the riser of cylindrical shape, and for the you can find this V by A to be minimum, or as A by V to be, V by A to be maximum or A by V to be minimum, you can have the condition that for which condition this for cylindrical riser, for what ratio of H and D the A by V will be minimum or V by A will be maximum. That condition can be found out, and it can be calculated, and it can be found that for H equal to D you get, suppose, that optimum condition. So, you need to design a riser for which, suppose, the H equal to D, and you want to find that for this casting of aluminum which is 15 centimeter a cube, in that case let us see how it finds. So, suppose it has again it is 6.5% of contraction is there. So, suppose for aluminum shrinkage is 6.7%. Now, if we assume that you take 3 times the volume required, as you know that this is the volume which is required for metal to be fed. Now, you assume sometimes empirically or sometimes just roughly they assume that you take 3 times the volume. So, if you take that in assumption, so the volume of this material for the riser that will be required as, so volume required for the riser it will be 3 times 6.7% of the volume of the casting. So, this can be found out, and this is computed out to be, suppose, 658.2 centimeter cube. Now, this is, suppose you have taken, based on the assumption that you take 3 times the volume of the shrinkage amount for just for being the safe side, and let us see if you design the riser based on that for a compact case for H equal to D, what will happen. So, for H equal to D, now if this is the volume of the riser, so for a cylindrical riser with H equal to D, so it will be pi by 4 H cube or D cube, and that will be 658.2. So, you can have D value, you can compute it, and this is computed out to be about 9.43 centimeter. Now, this is the diameter of the cylindrical riser, which is basically there, corresponding to, if you have taken the liquid metal to be 3 times the shrinkage which you feel, and which will be basically that is 6.7% of the volume. Now, we can find the A by V of the riser and A by V of the casting. So, suppose A by V of the riser, if we take it, A by V of riser, so A by V of riser will be 6 by D. When H equal to D, and when both the surfaces top and bottom as well as the curved surfaces are basically taking part in the heat extraction, in that case that will be A by V will be 6 by D. Now, A by V will be 6 by D, so that will be 6 by 9.43. So, 6 by 9.43, that will be 0.636. So, this is A by V for the riser. We can also find A by V of the casting, and if we find A by V of the casting, so A by V of the casting will be, A will be 6 times area. So, that is area of one face divided by the volume of the casting. So, it will be 0.4. Now, what you see is A by V of the riser is 0.636 and A by V of the casting is 0.4, and for meeting this condition that A by V of riser should be less than as A by V of the casting, we see that this condition is not met. So, even if you have sufficient amount of this volume of liquid metal in the riser, it does not ensure that this will. So, it in fact what you see is A by V of riser is, so A by V of riser is not less than A by V of casting. What does it mean? It means that riser will solidify early than the casting. So, even if you have sufficient amount of liquid metal, the volume sufficiency condition is met, this is seen that the riser is going to solidify early. So, that is not going to serve the purpose, and that is why this will not work. So, basically it has to see your riser, this one, this cannot be more than 0.4. So, once you give this A by V riser 0.4, from there you have to get the diameter of the riser. So, what you see is you can get the riser diameter by putting this value to the A by V, so that you can further find the value of the dimension of the riser. So, 6 by D has to be basically, so ideally 6 by D has to be less than equal to 4. So, that is what the condition tells, that is 0.4. So, D has to be more than, so D has to be more than equal to 6 by 0.4. So, that is D has to be more than equal to 15. So, at least you need a riser of diameter 15 centimeter for having the condition that it will solidify later. So, what we see is that it is very important to have these conditions meet, and also it is important to know that there are two requirements. One is the freezing characteristic of the material, which is important for calculating the dimension of the riser, whereas the sufficiency of the volume must be sufficient, so that the riser can basically see that it will be able to feed the liquid metal required in that case. So, what we have seen that these conditions are to be kept in mind, and then the riser volume is required to be computed. So, we will discuss the different methods which have been given by the researchers by doing certain experiments, and there are certain principles based on these characteristics, that how to calculate the riser volume required for feeding a casting, so that you ensure that there is no shrinkage in those cases. So, let us move to the different methods. So, one of the method which has been suggested, the first method is by Cain. So, that method is known as Cain's method. So, Cain's have given this condition given by one expression, that is x equal to A by y minus b plus c. So, this is the we see here this is a line which talks about the condition of the casting if the if you have the volume ratio is nothing but, so in the x direction let us have, the x direction is freezing ratio. So, basically it is representative of the freezing characteristics. We have seen that V by A or A by V talks about the freezing characteristic of the casting. So, V by A basically is proportional to, you can have that in mind, that it is somewhat proportional to, because T is anyway proportional to V by SA square. So, that way keeping in mind, so that its inverse is SA by V. So, let us say if the SA by V is taken, then this freezing ratio, it is ratio of SA by V of casting to SA by V of riser, or you can say V by SA of the riser to V by SA of casting. So, that way it is the x dimension is that, and the y axis, this is basically volume ratio, that is ratio of the volume of riser to volume of casting. So, once you have any casting, if you have the casting, now for that you have to calculate these freezing characteristic values, and this is basically SA by V casting, you know. So, you can have the surface area of the casting, you can have the surface volume of the casting. So, that is known. So, once you know that, you will have SA by V of casting. Now, find SA by V of the riser. So, for riser you have to have the condition known to you that what kind of riser you want to have. So, suppose you are taking a cylindrical riser with all its faces, you know, taking part in extracting the heat. So, if you take the cylindrical riser, suppose you are taking a cylindrical riser. No, now you can have the condition whether you can allow all the portions to extract heat, or sometimes, many times, what you do is, so you with all the surfaces the heat is extracted, but not from here, because we assume that the bottom part is in touch with the casting sometimes, either be the top riser or even the side riser. If it is in very much proximity to the casting, then this portion does not get involved directly. I mean, it does not aid in the transfer of heat from this face. So, you can have two cases. In one case you will have V by A is d by 5, in another case it will be V by A is d by 6. So, depending upon the situation you will have d by 6 or d by 5. Now, based on that, once you have that condition, you know this SA by V of riser also in terms of the diameter of the casting, and that whether HU and D of what ratio you are taking, that is up to you. So, that also again is on your choice. You are taking a cylindrical riser of H equal to 2D or H equal to D. So, once you know that, in the term of H or D, you know SA by V of riser. So, now you put in this equation x equal to, so you will have x equal to A by y minus b plus c. So, that is what the equation is. Now, in this equation you will have this equation, this is x and this is y. So, once you know this x you can compute, that will be in term of d, and then for that this equation is solved. So, you will put here in that equation, and then you find. Now, if the thing is, what we see here is that you will have to see. Now, this volume ratio of riser also can be found out, that will again be in the term of d. So, it will have that because you know the volume of casting and you know the dimension of the riser that you have assumed with one variable, that is d or h. So, that also known. So, that becomes an equation, and once you give that in equation you can solve it. Now, here these A, B and C are constant. So, for different materials you have different constant values. So, this becomes basically an equation, a polynomial equation, it comes out, and that needs to be solved for that value of d. So, that basically is solved normally, you will have to solve it, and that is solved by iteration methods. So, it will take time, but you can get the values. Now, this graph tells that if this, for any freezing ratio value, if the value comes out in this region, then your casting is sound. Otherwise, if it falls in this region, then your casting is likely to have the shrinkage. So, this graph is given by Cain's method, Cain, and that is why this method is known as Cain's method. So, in this, the advantage is that you have to solve an equation, but that is also the disadvantage, that this equation is a complex equation that needs to be solved by iteration method, and you can solve it. You will be given the value of A, B and C in the problem, so that you can solve it. We can solve these questions maybe in the next lecture when we solve certain questions. Next method is the NRL method, or Naval Research Laboratory method, or shape factor method. So, that is an improvement over this Cain's method, in the sense that there you have to solve a complex equation. So, basically that is replaced this freezing ratio term, which is there on the x axis. This term, this freezing ratio term, so that is basically replaced with the shape factor, and shape factor is nothing but L plus W by T. So, length plus width by thickness. So, once you know the length and width and the thickness of the casting, you find the value, and then you have a graph. That graph you can use. So, this is the graph which is proposed by the NRL Naval Research Laboratory, and that is why it is known as NRL method. So, once you know the length plus width by thickness, then for suppose here, if you come in between this, you can have satisfactory results, and if you come here in this region, it is sound casting, but if you fall below that, then this VR by VC for this, you will have the chances of porosity. So, that is why it is an easier method, because simply you have to calculate the length plus width by thickness. So, from there you will get VR by VC point. You can just refer this point, you may have a single line also. So, you may have a single line, from there you go there and you can have the satisfactory results. So, if you get that VR by VC, once you know VC, you can find VR, that is riser volume. So, this is a method which is used for calculation of the riser volume. Now, in this case, even the appendage volumes are also taken into account. Now, in this case, if the casting has appendages, they are also considered, considering towards calculating the total riser volume. So, in this case, what is meant is, because you have length, width and the thickness of the dimension, these dimensions are taken into consideration. So, you know the casting is taken as either a plate or a bar, that cross section. So, once you have that consideration in mind, then you have to have the consideration like what kind of appendage is there, whether main casting is plate and it is feeding the appendage volume, that is bar, or main casting is bar feeding to a plate, like that. So, in that case, that contribution has to be added to total riser volume. So, if you look at this, suppose the main casting is bar and it is feeding a plate, in that case by this curve, if the thickness parasite, so this appendage volume, suppose, so what happens, many a times you have a casting like this and this. Suppose you have a casting like this. Now, this is basically the main casting which is feeding these two. So, this is a case of, suppose this is a bar and this is a plate, or this is a plate and this is bar. So, this is a case of plate feeding bar, plate is feeding bar. So, what you can do is, first of all, you will have to find the requirement of riser volume for this plate. Suppose for plate alone, riser volume comes out to be VR plate. Then you need some extra material for the bar also, because this plate is feeding to the bar also. So, what you will do, you will use this graph, and what you will do is, you will find the thickness of this bar to thickness of this plate ratio. So, that is thickness parasite by thickness parent. Parasite means the appendage which is taking the liquid metal from this main casting. So, you will have the thickness ratio. Once you have the thickness ratio, then you go to typical curves. You have the typical curves as you see. So, this is a case of plate feeding bar. So, suppose thickness has ratio of 0.8, then for 0.8 you will see that you will have this point, suppose 50% of the 50% will be the percentage of parasitic volume. Means if the parasitic volume is, so if parasitic volume is suppose 50 centimeter cube, so extra 25 centimeter cube is to be added to VR plate. Okay? If thickness ratio is 0.8. What you see is that if the thickness ratio for the bar and plate is 0.8, in that case for this plate feeding bar condition 0.8 it is 50%. So that is why if its whole volume is 50 centimeter cube, in this you will have to add the 50% of this 50, that is 25 centimeter cube, and then the total riser volume will be required. So this method has that advantage also, that this is used for calculating the riser volume even in the case of appendages. Next method is, so even in that case sometimes for hollow cylindrical shapes, sometimes the shape factor, when you have the hollow projections, in those cases the shape factor is altered. So suppose you have a core in between, and depending upon the diameter of the core, this correction factor, so this L plus W by T, so shape factor L plus W by T, this is changed to L plus W by KT, and this value K comes from this table, because when you have a core, in that some effective surfaces, they are not basically can be seen, that they cannot be considered as the surfaces which are extracting the heat. So depending upon the diameter of the core, this correction is to be incorporated, and the value of K you can have. So in those cases when you have the core dimension is given, the external diameter and the internal diameter is given, so you know the thickness. So that basically if the core diameter is T by 2, thickness by 2, in that case correction factor is 1.17, if it is T 1.14 or so. So that is one correction which has to be put, correction factor is to be put in this method. The next method is modulus method. So what has been seen is that, as we know that T is proportional to V by A square. So suppose V by A term, volume by cooling surface area, this is known as modulus of the casting. So modulus of casting, it is defined as V by SA, V by cooling surface area, volume by cooling surface area. Now the thing is that volume, this term we discussed that for riser it must be more than that of the casting. So it was seen that the V by surface area, that is modulus of riser, if it is 1.2 times V by SA of casting, in that case it is seen that the casting is satisfactory. So what we see is that if you get this, so if you know the casting, if you have the casting with, and you know the volume and surface area of that casting, so based on that you can directly get the dimension of the riser. And if so, as you know that MC is the, suppose D by 5 is, so for suppose cylindrical side riser where you take height and diameter, and we discussed that if you are taking a cylindrical side riser and you assume that this part is not contributing, bottom part, only top part is contributing. So for that the volume by surface area will be D by 5. So D by 5 will be there. So this will be riser, and this will be 1.2 times volume by surface area of the casting, that is modulus of the casting. So in that case you directly get D equal to 6 times modulus of the casting. So you can directly get the diameter of the riser if you know, if you have the these volume and surface area of the casting known. So that this is another method which is there for calculating the riser volume. Then you must know also the feeding distances for plates and bars. So, that is very much clear that once you have the riser, how much, up to what distance it will be able to feed the liquid metal. So, that for suppose it is a plate casting, as you see that you have the maximum distance in one side is 4.5 T. So, that riser contribution is 2 T and the edge contribution is 2.5 T. So, this way you can say that you have this amount, that is riser contribution as well as edge contribution for a plate dimension. So, if you keep two risers in between, as you see riser contribution is 2 T and 2 T from both the sides. So, it will be 4 T here, and then this side you will have the edge contributions. Similarly, you will have the, for plates when you use the chill, in the case of chill you will have the extra contribution by the chill. So, extra contribution by the chill is given as 2 inch. So, 4.5 T was earlier and you have the chill 2 inch. So, and if you place the two risers, you see that 4.5 T this side and this side and 2 inch both because of the chill. So, this way depending upon where to place the riser, so that your casting is completely fed and it does not have any kind of thirst, it does not have any kind of shrinkage defects. That has to be seen by looking at the dimension of the riser, the how much distance, because if there is small distance left you can use the chill, but if the large distance is left you will have to increase the number of risers. So, number of risers also can be decided based on that. This is for bars. For bar it comes out to be 6 root T on one side, and then if you use the chill in the bar also it will be plus T. So, this is how 6 root T on both the side if you have the two risers. So, if you have maximum you can feed 12 root T, and if you use a chill 12 root T plus 2 T. So, this is how the feeding distance is defined for bars and plates, and you can see that you can ensure that how many of the risers are required to be used for these. You can use the feeding aids for increasing the efficiency of the risers. Feeding aids means those medium by which the riser can be seen that it can be used for longer time. So, where the liquid is for larger time. So, you can use the padding method. In padding you use the excess of the metal, so that the solidification time increases, and that is used normally in case of wheels, casting, for crane wheel casting, where you use the metallic padding. Or you can use the exothermic materials also, anti-piping compounds in the riser, so that in the riser the liquid metal is there for longer time, so that by using these feed aids the size of the riser even can be minimized or decreased, so that the riser effectiveness is not decreased, or if it is higher. Thank you very much.